In this project, I've decided to analyze the stresses on an anvil mounted to a wooden post in my yard. As you can see, the anvil is not being secured by 4 traditional bolts as my model suggests. I am instead solving the system for the idealistic 4 bolts necessary to hold this anvil down, as the original bolts securing the anvil have since failed. The post is made up of 2 pieces of pressure-treated pine which have been bolted at their center. I don't believe there would be any significant stress at the bolts securing these posts to each other, at least not by comparison to the bolts holding the anvil to the post. Because of this, I will ignore the fact that each post is separate, and I will consider them one large post, which is 18 inches wide by 25 inches tall. My calculations are assuming that I have a 5-pound hammer. This is a 3-pound hammer. The heaviest hammer that I own is 5 pounds, and I have never used it. I do that just to give me an idea of the maximum force to pull these bolts out. As far as the last of the materials go, the anvil is cast iron, the bolts are all galvanized steel, or at least ideally, and the hammer is steel. There are compressive forces present between the anvil and the post. As the strike force causes a bending moment, a compressive force is created between the anvil and the post as the anvil tries to rotate. There are tensile forces in the bolts. There are hammer forces acting on the horn or heel of the anvil depending on where the hammer is struck. There are normal forces opposing those strike forces. To find the strike force, I multiplied mass by the change in velocity over the change in time. This got me 204.3 newtons. By standard graphing conventions, the strike force will be negative since it is in the negative y direction, and the normal forces will be positive 204.1 newtons since they are in the positive direction. To find the bending moment of each, I just multiplied the strike force by the distance of the strike location in meters. To find the horn stress, I first needed to find the area of the striking surface of the anvil, excluding the heel. I got 4.6736 meters squared. Second, I found the moment of inertia, which was 24.925 meters to the fourth. Then I found C, which was just 4 inches, or 0.1016 meters. Now that I have these values, I can plug them in for our stress equations. Axial stress, which is normal over area, is 43.713 megapascals, and bending stress, which is the moment times C over I, was 0.2961 megapascals. Now the process to finding the heel stress is virtually identical. I first needed to find the area of the striking surface of the anvil, excluding the horn. I got 4.4704 meters squared. Second, I found the moment of inertia, which was 23.842 meters to the fourth. Then I found C, which was likewise just 4 inches, or 0.1016 meters. Now that I have these values, I can plug them in for our stress equations. Axial stress was 45.700 megapascals, and bending stress was negative 0.2874 megapascals. To find the force in each bolt, we first need to find the distance from the center to each bolt. This will be the same for both the horn and the heel. This is the square root of 0.1524 squared plus 0.1016 squared, which is 0.18316 meters. The force of each bolt is calculated with m over 2r. This means that the horn bolts will be 198.294 newtons, and that the heel bolts will be negative 184.151. From what I can find, a pretty standard cross-sectional area for a bolt in this application would be 5 times 10 to the negative 5. Dividing each force by our cross-sectional area gets us the actual force of each bolt. For the horn bolts, we get 39.65 in tension, and for the heel bolts, we get negative 36.84 or 36.84 in compression. The bolts in this system should only fail when the applied stress exceeds their yield strength. From what I can find, galvanized steel should have a yield strength of about 250 megapascals, which far exceeds the applied stresses, so the system should hold. However, this differs from my own experience. Although the wood was pressure treated, it is very possible that some of the natural degradation in the wood may have inspired failure. Likewise, fatigue from vibration and odd hammer strikes could have also affected the original bolts. I believe that this system is much more complex in reality than the ideal problem I'm solving for. To summarize, the system that I solved for doesn't actually account for every single factor causing these bolts to loosen. For example, this isn't doing anything apparently. It was when I put it in there a couple of years ago. Everything else in here is just added supports. It could be the wood splitting, the wood breaking, the wood rotting, vibration. It could be any other number of things that I have not been able to solve. The system I solved for only accounted for uniform strikes to the same location on the horn and the same location on the heel, which idealistically it shouldn't fail under those conditions, but in reality it did.